I'm going to say a few more words about Dr. Luke Barnes as he's setting up his computer here, and we're transitioning. I've known Luke for a number of years now, and significantly, a couple of years ago, about 3 years ago now, he wrote this book, Fortunate Universe, Cambridge University Press, which is where he got his PhD, and he wrote it with an atheist. And in it, though, they make the argument that the universe has all these special properties that allow it to be life-permitting. You change these constants a tiny amount, and it's not. That's the basic thesis he'll get into some here in the presentation. But I just wanted to mention, I went around with him to like 5 different universities in the Texas area alone, and saw him interact with like philosophers, skeptics, top skeptics at universities. And he just did an incredibly great job at answering the objections and interacting with them in a winsome way. And really, I think he is probably the top expert in the world on fine-tuning, at least at the fine-tuning argument for God. He's got 7 peer-reviewed papers on fine-tuning, some scientific, some philosophical. He's got the philosophical acumen to analyze that aspect as well. And so I think this argument in particular is one that the naturalists have a difficult time with, because it's right there at the very foundations of physics. You're looking at the bottom level and analyzing all these special properties. So they can't appeal to evolution, they can't appeal to naturalistic processes to explain the constants and initial conditions of the universe itself. So it's a very powerful argument, and he's going to give us a bit about that now. So I'll turn it over to Luke here.
All right, well, good evening. I feel a certain affinity as an Australian with Texans. I feel like the rest of the world wants us to say hello in a certain way, right? I could say good day, you could all say howdy. I think we're all better than that, so thank you for saying good evening. It's great to be back in the US, and it's great to be talking to you about this particular book. Now, I just want to take one part of the book and just expand it out for you. I don't want to give you the whole thing. I don't want to give the whole story away, because then why would you buy the book, right? I mean, sure, there's other authors, but I want to take one bit of the book. I want to particularly answer this question: how did the universe make order from chaos? And I want to look in depth at this question, and I want to start, as all good scientists should, with a basic observational fact about the universe. We're going to start with one thing, and we're just going to follow it as deep as we can go with this one fact, and I think we end up somewhere pretty interesting. Okay, this one particular fact about the universe is one that you're all very familiar with. It's that you can start a fire with a match. There is my observational fact, okay? So if you have some wood and you want to, no expense spared, if you want to create a fire, all you need to do is just sort of drop a match on. And then what it will do is, over the course of however long the fire goes for, it will turn this lovely pile of wood into that pile of ash and produce a whole lot of light and heat in the process. That is our observational fact. I'm sure you can try that at home. Be careful. The reason why that's kind of interesting as a physicist is that there is nowhere in the supermarket where you can buy an anti-match which goes back in the other direction. There's nothing you can buy from a supermarket which you can strike, throw onto a pile of ashes, and oh, hey, wood, right? That does not happen. It has never happened. If you think that's happened, then I can't help you. It hasn't happened. What this is reflecting is that in our universe there is this thing we call energy, of course, but energy has different qualities to it. There are more and less useful forms of energy. Sometimes there's energy where in the form of the wood, in the form of the chemical bonds in the wood, which is very easy to turn into other forms. I can take that form of energy and I can make heat and light out of it, and I can turn it into this less useful form. This is something that physicists really started noticing, the fact that certain processes go one way in time but never in the other, around about the time of the Industrial Revolution. They wanted to make more efficient factories, so if you wanted to take your factory, put a whole lot of coal in at one end and do whatever it is a factory does, and out comes a snowmobile at the other end. That was obviously the first bit of clip art that came up in the program. What you do, that's absolutely fine. That will work, and that's something that sort of powers the world around us. If you want to make a coal factory, Don't go burning snowmobiles, okay? Don't try it backwards. There are these more useful forms of energy and then there are less useful forms of energy, and it's from this fact we're going to head towards where I want to get us tonight. Because every time, when scientists looked in detail about this, physicists looked in detail as they were forming the laws of thermodynamics about how heat does what it does in the universe, they discovered the second law of thermodynamics, which is that energy is always turning from more useful into less useful forms. So whenever we see energy transforming, and we see it transforming from in various forms from one to another, it will always be the case that it's going from something more useful to something less useful. And we always find that kind of transformation happening whenever in the universe we see a process which will go one way in time but not the other. Anytime you see something that looks really weird in a video going in reverse, you're seeing something that's a consequence of this second law. This is so basic to the world around us that we barely notice it. So, for example, if you want to smash a glass, you simply throw it at the floor. Okay? Not the first slow motion video in this talk, so I look forward to the next one. Okay? If you want to smash a glass, just throw it at the floor, and it will make the sound of breaking glass, and all the pieces will fly out all over the place, and that's how you smash a glass. If you want to repair a glass, here's what you don't do. You don't throw all the bits and pieces of glass around on the floor and then make a sound with your mouth like glass shattering but in reverse, and hope that as all the pieces sort of come in and collide together, that, for example, this piece is just rotating at exactly the right speed to go into exactly the right point, and the sound you made will come exactly in at the right time to fuse it all together, and we're waiting for the crack to happen in reverse, so let's all just watch that for a second. None of you are listening to me right now. We're all just waiting for it. I love it every time. Yeah. Random science fact for today. Cracks in glass move astonishingly quickly. Anyway, that's all. How do we understand this fact? Especially in terms of what we think are the basic bits and pieces of the universe. So, as usual, as a physicist, we now start talking about a box with some gas in it. If you're familiar with physics, we're always talking about a box with some gas in it. How can we arrange this box with some gas in it so that it has some useful energy, right? What is it about the arrangement that makes one useful and another not useful? Well, consider a box where you've got everything on one side and a divider in the middle, and here's what you're going to do. You're going to put a wheel on the top and then just slowly let the gas flow from one into another. And so what actually happens is, as they flow, it will turn the wheel. No expense spared on the special effects. Here's what that tells you. What that tells you is that this is a useful arrangement. Anytime you can take an arrangement of the energy in the universe and turn it from one form into another, turn that energy from one form into another, turn the energy that's from these gas particles bouncing around and turning into actually turning a wheel, then you've got something which is a useful arrangement. If, on the other hand, you don't have that thing down the middle, you've just got a box of gas and you've got a wheel there, you have a useless arrangement. And the reason is you need to turn that wheel in a certain direction. But if there's a whole heap of gas in this box, for every time it gets hit one way by something, on average, it won't be very long till something hits it back the other way, they cancel each other out, the wheel does not turn. So this is a useless arrangement. And in particular, what was discovered towards the end of the 19th century is that one of the key features of this useful arrangement we can understand as follows. Suppose you have, well, there are 24 particles there, and you want to put them in the box in this useful arrangement. But you have to do it by flipping a coin. You're going to flip a coin, and if it's in heads, you put it on one side, and tails, you put it in the other. If you want the useful arrangement where they're all on this left-hand side, you better get 24 heads in a row, okay? There is precisely one way of doing that. They all have to go to the left, so you get, of all the ways you could do that, one useful arrangement. Okay? You didn't think you were getting a thermodynamics lecture tonight, did you? We're in the middle of it. If you're, on the other hand, you're thinking you want to get about half and half, the useless arrangement, well, there's loads of ways you can get that. Like, you could split them up in this way, or you could split them up in that particular way, or you could just pick any of the ones that you like. You've just got to, if you're flipping this coin, get roughly as many heads as tails, and that's, the most likely thing to happen. So, for example, in this particular case, check my maths later. It's not too bad, but anyway, 2,704,156 useless ways to arrange the system. And so starting with the work of the physicist Ludwig Boltzmann in the end of the 19th century, they sort of realized what was going on behind this whole useful energy versus useless energy thing. Okay? Where you have useful energy, the micro details of the system you're talking about is in some sort of rare arrangement, a special arrangement, one you're probably not going to get if you're just flipping coins and throwing stuff around at random. If you have useless form of energy, right, you have something that's in a very common arrangement. And so with this understanding, the second law of thermodynamics, which we understood from, just trying to burn coal to make snowmobiles as being more useful into less useful forms of energy, just means that the universe is going from, the system, is going from a rare arrangement to a very common arrangement. And that, in fact, explains why the second law works in some sense. If you take a rare arrangement and you just jiggle it around a bit, you'll probably get one of the more random common arrangements, and so that's how most things evolve. On the other hand, one of those common arrangements, if you start with one of those, they'll probably just turn into one of the other common arrangements. If you just randomly throw stuff around in this box, chances are half's going to be on one side, half on the other, and that's the way it's just going to stay. This creates a puzzle, and a fundamental puzzle that points us back towards the beginning of time. In fact, it's this. Why is there any useful energy in the universe at all if these useful states are so rare? If you just sort of throw your universe together, all right, why is there any useful energy in the universe at all if those are precisely the rare states? And as physicists have thought about this for the last sort of 100 years, and especially in the last probably 30 years, it really comes down to only one answer as a physicist. You need to assume something about the way the universe began. And it's going to sound like a cheat, but here is sort of the cutting edge of how we answer this particular problem. It's called the past hypothesis. The universe began in a very rare arrangement with loads of useful energy. Does that sound like a cheat? But that's really the only thing that we can do. Here's the reason why. If I trying to explain the way the universe is now, right, today, here in this room, but I know about the second law, and so any state in the past that I point to say, hey, that state in the past is going to turn into this state here now, that has to be a more special state in the past. And then if you think about that state, and you go back even further, right, the same thing happens. And the further back you go, the more order you have to find. Because if you ever stop and try to turn this thing around and say, oh, I know, I'll before that one, I'll put one with less order, right, you get a beat down from the second law of thermodynamics, which says, no, that's not going to happen. And precisely what that second law is saying is if you start trying to say, oh, I'll get some less order and turn into more order, precisely what the law is saying is that process that you think will happen won't actually happen. Something else will happen. You think we're going towards a rare state. What actually is going to happen is, as usual, you're going to a more common state. That doesn't happen. I need to just take a little bit of a detour here for one slide. But the good news is it's the other slow-mo video. Here's a simple experiment. So this is water, and then they've put some ink in a syringe and then just shot it into the water. It's a good one. If you haven't discovered the slow-mo guys on YouTube, then just enjoy yourself later on this evening or tomorrow. I've been talking about order. And by order, I mean something very specific as a physicist. Whatever it is about the arrangement of the universe that makes the energy useful. There is another thing we could be talking about the universe, which is complexity, which is something else, which is about how much information it takes to specify a certain state. So I've just shown you this very simple experiment. Now, this experiment does not, in fact, violate the second law of thermodynamics, because none do. Okay, so that's why it's called a law. Okay, so this, like everything else, is an example of something going from a more orderly to a less orderly state. Because everything you've ever seen in your entire life is an example of that. Okay, unless you're watching a video in reverse. Okay, But if we think about complexity, we're thinking about how much information we need to describe a system. And when we started off, I'll show it again because it's fun. We started off with a simple thing to describe. We've just got some water and some ink in a syringe. And they're British, if you can hear the, look at that. If we just let this video go, if you come back in half an hour, and you would also have another simple system. You would have a inky blue water, right? It would just all be mixed in. So we started with a simple system, and we ended with a simple system, and in the middle we got this complex state, which would require an awful lot of words for me to describe. Awful lot of information is there on the screen. There's no simple way to describe in detail what's going on there. Right? So once we've pulled those two ideas apart, complexity and order, there's no second law of complexity. Right? You just saw it go up and then go back down again. Okay? I can show that to you on the screen, but that is not about, that's not what I'm talking about here. I'm talking about the order that makes energy useful. What this means in particular is that I can start from energy as we see it in the universe today, and I can run the cosmic clock backwards and tell the story in reverse and find those more useful forms of energy that we had in the past. Okay? So let's start with a really simple system. Let's start with, say, some ice in a glass that is slowly melting. Okay? That, like everything else, is a case of something more orderly becoming less orderly. But as we sort of hit reverse on this and think about what came before the ice, we can go backwards in time. You can't point at the screen, never mind. The ice in the glass, obviously the ice came from a freezer of some sort that runs on electricity. Electricity, well, at least in Australia, we get it from burning coal. Yeah. I would leave that. Good. So in particular, the coal, as I said, I mean, it has other effects, but it is an incredibly condensed form of energy that's just ready to release, like wood. It'll burn with just a match. Coal is sort of laid down, it's sort of condensed sunlight, is the short story. You can go and talk to your favourite geologist about why that happens. So the short story is that most forms of energy on Earth eventually came from, have their origin in sunlight. So why is sunlight a particularly useful, particularly orderly form of energy? Well, we can think about one photon, one particle of light just heading from the sun towards Earth. And in that one particle of light is so much energy that when the Earth sort of re-radiates that, it will re-radiate 20 lower energy forms of particles of light. So we took that one condensed, super useful one particle with loads of energy that can do lots of stuff, and we turned it into 20 that sort of all headed off in different directions. And if you're wondering why that seems orderly, think about trying to reverse that process. You've got to go collect a lot of photons from all over the universe and send them back towards Earth and hope that that's not going to happen. Why is that one photon of light particularly useful? Well, there are nuclear reactions at the core of the sun. As I illustrated here, we have two protons forming deuterium, which heats another proton, which forms helium-3, and then another chain produces another helium-3, and at the end we get helium-4. That is the answer to the question posed in the rhyme, Twinkle, Twinkle, Little Star. Okay? That's what you are. I'll wait for the right-hand side to catch up on that joke. Good. For every one of these, there's enough energy for 1 million of those. Okay? So if you've got 4 protons there and conditions hot enough to whack them together to make a nuclear reaction, you can produce 1 million photons from the sun. So obviously this is the condensed, highly, the useful form of energy that we can turn into other forms. Why is the sun? Why are stars a particularly useful form of energy? Well, stars form as gas clouds collapse, and so why is that a particularly useful form of energy? It's precisely because under the influence of gravity, there is an awful lot of gravitational energy here ready to be turned into heat, which then turned into nuclear reactions, turned into photons, and then off we go down our story again. So because the universe has these sort of spread out clouds ready to collapse and ready to release that energy, that's how a lot of the energy in the universe today was if you sort of go backwards in time. And so if we go back to the sort of universe as baby pictures, this is the cosmic microwave background. It's a picture of the universe very shortly after the beginning. And by very shortly, I mean very shortly to a cosmologist, 280,000 years. We see a universe which is almost perfectly smooth, okay? And under the force of gravity, any sort of lump and bump here can collapse, and so there's loads of useful energy here ready to go. Every time these collapse, right, a lump of these, you can make a whole boatload of stars out of that, which will power whatever you like for an awfully long period of time. This is the useful form of energy at the start of the universe, as best we know. And so we can actually hit play on the universe and see how it plays out after this, and this is part of what I do for a living, which is kind of amazing. So what we can do as a cosmologist, as a theoretical cosmologist in particular, we can simulate a part of the universe in a computer. And it's simple. Have a go at home. Yeah, good. We take a piece of the universe. We know the universe is expanding, so we can put that physics in. And then we split the matter in the universe up into sort of pieces that are going to represent a certain amount of mass. And then you program into those pieces will feel the gravitational pull of each other. If they are gas particles, they will also feel pressure forces. When they are hot, they will glow. When they become very dense, they will form stars. When those stars reach the end of their lives, they might blow up as supernova. And all of that we stick in a computer. And if you tried to run this simulation I'm about to show you on that computer, it would take 500 years. So we don't do that. We let sort of 5,000 computers have a go at it for a month and a half. And then we make a nice movie that you're all now ready to appreciate. So here is the story of the cosmos. Here is how structure forms in our universe. Starting from that almost uniform beginning, as things start to collapse under gravity, we get structure forming, the densest bits of the universe become even more dense, and we see dense knots starting to appear where galaxies will form. There, the density of gas is high enough to make stars, and you can even see, if you look closely, supernova explosions going off and pushing gas back out of the universe. Gas enriched with the heavier elements produced in stars, which we actually find in between the galaxies, which is cool. As time goes on, we see this sort of structure where you have cosmic voids, where gravity has emptied them out. We see the dense knots of matter which form galaxies and clusters of galaxies, and in between these filaments of the cosmic web, which haven't quite decided which way they want to fall. That is the story of the universe running forward. And it starts off with that useful energy at the start, which you just have to stick in there from the start. So let me underwrite the point of how ironclad this is, in a sense. So here's a quote, one of my favourites, from a British astrophysicist from the last century called Arthur Eddington. And he was talking about what do you do as a scientist when something looks like it's going to contradict your theory. So here's what he said. He said, if someone points out to you that your pet theory of the universe is in disagreement with Maxwell's equations of electromagnetism, well, then so much the worse for Maxwell's equations, okay? If it is found to be contradicted by observation, yeah, well, those experimentalists do bungle things sometimes. But if your theory is found to be against the second law of thermodynamics, I can give you no hope. There is nothing for it but to collapse in deepest humiliation. Okay? Whenever you think you've had some sort of profound thought as a Christian, there's a clock starts. And there's a certain amount of time until you find out that C.S. Lewis already said it. So, here we go. This is basically everything I've been trying to say, and as usual, C.S. Lewis says it in 2 sentences a whole lot better than I could. If a man says Humpty Dumpty is falling, you see at once that this is not a complete story. A nature which is running down cannot be the whole story. If a nature which disintegrates order were the whole of reality, where would she find any order to disintegrate? Okay? There is a tradition, a sort of trend that I've noticed amongst, and a bunch of people have noticed, amongst the peer-reviewed literature in astronomy. And it goes like this. Whenever the title of a paper is a question, the answer is no. How did the universe make order from chaos? And the answer to that is no. The answer is it didn't. That is not the story of the universe. The story of the cosmos is this. Every successful scientific explanation of some fact about the universe assumes an orderly special past. There are two types of theories about the universe. There are those which assume an orderly and special past, and those that are wrong. Okay? Anytime any scientist has done their job properly, they have assumed an orderly beginning of the universe. It is just, you just have to lay it down at the start, otherwise you run up against one of the most solid pieces of information we have about our universe, the second law. So let me polish this off by just explaining how I fit some of this together into sort of a bigger picture. So that's I think you've just heard a lecture on the statistical mechanics, so fantastic, enjoy yourselves. How I fit this together into sort of a larger picture. I was in Brisbane in Australia last year where we had a conference on science and religion that I was talking at, and as I was walking to the bus, unfortunately I was late, so I couldn't stop to say hello and introduce myself to the man who had the following shirt on. It said, "Too stupid to understand science, why not try religion?" Desperately wanted to introduce myself, but unfortunately had to catch the bus. I think as I've tried to understand the sort of thought behind this, there's a picture of how the sort of history of science that goes a bit like this. So we used to believe in a whole load of gods, and we used to think that they controlled the universe, right? So when there was a thunderstorm, there was a god who was cranky, and it was a sunny day, they were all happy, and all those sorts of things. And then we discovered that actually, rain and lightning and all those things, actually these were natural processes. And so science discovered the way that these things work, and so we put God out of a job. And that was all very sad for a whole lot of people. I can see that's making some people sad. And so that's the sort of picture that you have of the gods, that they have been put out of a job, and so there's nothing less for them to do. The problem with this picture is that it is a picture of the gods which is not the picture of God that we have within the Christian tradition, within the Jewish tradition, within actually an awful lot of traditions. There's a picture of gods here which are sort of these small g gods. And if you start with a god who is finite, if you start with gods who are just creatures, who are imperfect, if you have a whole lot of gods, just many of them, if they're all sort of short-tempered and cranky, and if they're ultimately whole load of them are evil, then the world that you end up with, don't be surprised if, because it's finite, there's no reason why those gods are there, right? And so the world is ultimately inexplicable, right? There's no ultimate reason why those gods are there. You've just pushed the problem of why the world is there back to the problem of why the little g gods are there. Because they are creatures, there's no ultimate creator either. I mean, you can ask where they came from, and for a whole load of the gods, it's from Mr. and Mrs. God, but beyond that, there's not much of a story there. Because they are imperfect, the world you will see is ultimately unpredictable, right? Who knows whether the thunder god is going to wake up cranky tomorrow, so good luck with your weather forecasting. Because there are many gods, we could see a patchwork of different laws, right? There could be, one god working over there and another one over there. And because they're short-tempered, we would expect them to sort of mess with the world. And because they are, many of them, ultimately evil, we would expect an ugly world. If you read, for example, the Babylonian story of creation, you find out that the world is sort of the leftover carcass of a dragon repurposed into the heavens and the earth, right? So what is the world we see around us? Repurposed dragon carcass. Are you expecting to see great and wonderful, beautiful things? Obviously not. It's going to be a sort of ugly place. On the other hand, if you have a different picture of God, if the God that you think is there is one who is, first of all, ultimate, where all explanations stop, who is the kind of a thing that is a mind, or at least more like a mind than anything else we know, who is truth, who is where all truth finds its source, who is one God, there is unity in being, who is free, and who is goodness itself, then the world that will come out of that will be a number of things. It will be dependent on the ultimate explanation. It will not just exist in and of itself. It will be orderly because there is a mind behind it, as we heard before. It will be consistent because its author is the author of truth itself. It will be coherent because there is one God. There isn't a different God over there and over there. It will be contingent because God is free. There will be nothing about the universe which has to be some way rather than some other way because God was free to create whatever universe that he wanted. And because God is goodness itself, we would expect the universe to be beautiful. And so if you're living in that kind of universe, wink, wink, nudge, nudge, when you go to do science, you'll simply be looking at that universe. And so the science that you will end up doing will look a lot like this. You will be doing science and not metaphysics. You will not answer ultimate questions of existence just by looking at the universe because that's not where the answer is. You will find a universe, however, which your science will be rational. And you will need to get your brain in gear if you're going to start looking at the universe and trying to work out what happened. You will need to be inductive. What that means is you will need to go and look at the universe around you. But if you do that, there will be patterns for you to see. It won't be different, every second Tuesday, gravity takes a holiday. You will be able to take a small set of observations and, if you are careful and you do everything right, generalize to how the universe is. We will find laws because there is a coherent story of the universe. We will find that you have to be empirical. You can't just sit on your armchair and reason about how the universe must be. Okay? We can all just sitting in here right now with a paper and pencil and a couple of attempts, we can all do some mathematical, calculation. 75 times 20. We can all just sit here and eventually some of us will do it. Okay? But you cannot sit in this room with a piece of paper and answer the question, how many moons does Saturn have? Right? You have to go and look. And that's the kind of universe we're in. You have to go and look about what it's like because it is the product of a free mind. It could have been otherwise. You can't read God's mind without actually looking at what he did. And we will find scientists again and again commenting on how beautiful and how deep and how elegant the universe is. There's a wonderful letter from Heisenberg to Einstein saying that we find in nature these laws that even Plato could not have comprehended how beautiful they are. And so within this picture, we also find, I especially want to go after this first point, when we have done our science and done it properly, we will find that it is pointing to a whole load of deep questions. Right? I love this particular quote. It's by David Albert. It's a bit of a mouthful, so I'll break it up into pieces, but it's saying something extraordinarily important. He says, the fundamental laws of nature generally take the form of rules concerning which arrangements of the elementary stuff are physically possible and which aren't, or rules connecting the arrangements of elementary stuff at later times to its arrangement at earlier times. Okay? The laws take that form. How can you arrange the stuff? And how does the stuff today follow from the stuff where it was yesterday? But what that means is, or something like that. But the laws have no bearing whatsoever on questions of where the elementary stuff came from, or why the world should have consisted of the particular elementary stuff it does, as opposed to something else, or why there should have been a world in the first place. Once you've done your science, you will be staring those questions in the face and science will not have answered them for you. And so you can either try not to answer them really hard, or you can look for an answer. So the choice I want to put before you, and the choice that I hope the book consistently puts before you, is not a choice between science and God. Science fits beautifully within the Christian worldview. Of course, if there's a rational creator, we can look at creation and see something of what the order in there is. The choice is between God and naturalism, this idea that the universe is all there is, and all these questions, right, we just have to try and forget that we ever thought of them. Okay? The point is not that the naturalist has one set of answers and the theist has one set of answers. It's that the theist has one set of answers and the naturalist is trying to convince you that these are not really questions at all. Okay? And so you have a choice there. And it's a choice where various people fall on various sides and you will just have to weigh up the evidence. But hopefully I've put them before you today. So let me finish with just one thing. the real point I want to hammer home is this important thing about the story of the universe. Okay? Whenever someone says the story of the universe shows how order came out of chaos, then they are breaking the second law, and it is the physics equivalent of a piano falling on your head. It is completely wrong. It's not a good outcome. The story of the universe is one in which there is order from the beginning. And once we start staring that in the face, and the other fine-tuning things that Al and I have talked about, and all the rest that's in this book, once you start staring at those, you can start weighing up these options of what we are going to think about the universe as we see it around us. So I'll finish it there. Thank you.
Thank you all for coming tonight. I appreciate it. It's been a wonderful thing to have everybody come out. I was very pleasantly surprised with the turnout. It's been fantastic. You got hit with a lot of science and philosophy tonight, and it may seem over your head, but the book is very readable. These people that have contributed, have spoken in front of large audiences, and have broken down the concepts very eloquently and simply, and Luke's chapter is just as enjoyable as listening to him. So now you've got a voice as you can read along as with it and imagine Luke. I want to read something from my chapter. This was a quote from a science writer, Jim Baggett, and it kind of sums up what we're talking about. Whenever historians examine the details of scientific discoveries, they inevitably find only confusion and muddled vagueness and error, good fortune often pointing the way to right answers for the wrong reasons. Occasionally they find true genius. Theorizing involves a deeply human act of creativity, and this, like humor, doesn't fare well under any kind of rational analysis. The knowledge that science can be profoundly messy on occasion simply makes it more human and accessible, more Kirk than Spock. In other words, the science involves creativity. Science involves the imagination. Science is messy because it's a human endeavor. And as Luke said, we wouldn't even have science if we didn't assume a kind of order. So hopefully our book talks about how the universe is orderly and points to the glory of God.